Hello, tonight we're going to solve problem 51, chapter 6, Holiday Resnick Walker's 7th edition, Fundamentals of Physics. Now here we have a mass orbiting about a rod. So if you're reading the problem, these are the givens and there are several unknowns, parts A through D. So let's start out with part A. We're going to add up all the forces in the x direction, set it equal to 0, and we're going to add up all the forces in the y direction, set it equal to 0. Now, the net force in the y direction is equal to 0, but notice here that I'm using a pseudo-force method. It may not be obvious to you, but the sum of the force in the x direction do not equal to 0 in the conventional sense, because our convention in uniform circular motion is to identify the centripetal force. But I'm going to use the pseudo force in this problem. So bear with me, and then when I go the conventional, I'll let you know when I use the centripetal force. So identifying the vectors in the upper and lower strings. Here are the x and y components of the upper string, and here are the x and y components of the lower string, and I'm showing them in proportion to the force of the upper and lower string. Showing the weight of the ball, okay, down, and I'm going to show the centrifugal force to the right. Now labeling these vectors, we have mg, the centripetal force. We have T1, T1y, T1x, T2x, T2, the tension along the string itself, and then we have T2y. Now let's start with the sum of the forces in the x direction, and we have 3, so that would be minus T1x plus minus T2x plus the pseudo force, F sub c, that's equal to 0. So expressing T1 and T2 in terms of an angle, and that angle will be the angle between the upper tension and the horizontal. And we've identified this to be equilateral triangle, so each of these angles are 60 degrees, therefore theta is 30, so half that. So T1x is T1 cosine theta. T2 is T2 cosine theta, and Fc is mv squared over r, the centripetal force, but in this case the centrifugal force. That's equal to 0. So part A asks us for the tension in the lower string, and it appears from this expression we can't get there from here. We're not given the speed of the object. So let's look at the sum of the forces in the y direction. And let's see here. We have T1y up plus minus T2y down plus minus mg. And it looks like we're good here. It looks like there's enough known values to solve for the unknown T2. So expressing T1y in terms of the sine of the angle, we have T1 sine theta minus T2 sine theta minus mg is equal to 0. So hold on to your hats. I'm going to solve for T2, which is the tension in the lower string. We should get T1 sine theta minus mg over sine theta. Now plug and chug with the known values, T1 and the angle 30 degrees, g is 9.8. We get 8.74 newtons, and that's consistent with my diagram. I'm showing a vector shorter than in the lower string than the upper string. So a difference between 35 newtons and 8.7 newtons is consistent with the diagram. Now, that's part A. So part A, we needed the sum of the forces in the y direction. Part B wants to know the net force on the ball. And the net force on the ball in the y direction is 0. Okay, the sum of those forces equals 0. the net force on the ball in the x direction, I have to go to the more conventional approach, and that is to say that f of x, the sum of the forces, in this particular, the uniform circular motion in the horizontal plane, is equal to ma sub c, where ma sub c, the centripetal force, points radially inward. Now, I've already accomplished this task up here, but the fc is to the left of the equal sign. So if I were to rewrite this expression, we would have t1 cosine theta plus t2 cosine theta is equal to mv squared over r. Now, we have enough information now to solve for the left-hand side of the expression. If you substitute 35 cosine 30 plus 8.74 cosine 30, you're going to get a force of 37.9 newtons. And that's equivalent to mv squared over r, which sets us up for part C. Now I'm going to eliminate some of this to make up some room. So say goodbye to part C. You can always bring that back by reversing the video. So I'm just going to nix that out. Let's see, I guess, I don't know where that came from. So anyway, let's move this up. Let's see if I'm successful moving this up away. So, whoops. Okay, hold on. One more shot. Okay, yeah, we can move that up there, that whole deal. And let's see. So, so part C wants to know what the speed is of this orbiting mass. So we have the net force along the x direction of 37.9, and that's equal to mv squared over r from part B. So again, sleight of hand, hold on to your hats. The speed is the square root of r over m times 37.9. Take the square root of that. Now r you can find by using tangent theta. I'm going to solve for r here. The tangent theta is opposite over adjacent, therefore r is equal to d over 2, which is half that rod's length between the two attached points, divided by tangent 30. So there you have it. And r is equal to 1.47 meters. So so that's the speed. Oh, let me give you a magnitude so you can check with your work. The speed is 6.45 meters per second. Now, part D wants to know the direction of the net force, and along the y it's 0, but along the x, the net force is directed radially inward. So there you have it. Best of luck with the other problems, and I hope you have a chance to view this tonight. I'm a little late, and I apologize. So have a good evening.